Okay, welcome everyone. This is Bob at ScyllaDB, and I'll be your moderator today. I had the pleasure of introducing Kyle Kingsbury as a keynote at our Scylla Summit just a couple of weeks ago. And he had to try to cover all the things he had done with Scylla in just a 20-minute talk. Well, our audience rated Kyle's keynote as the best session at our conference, and that's across dozens of great sessions. So we are very glad to have him back today so that he can spend more time going into the details of his testing suite, his methodology, what he found in Scylla, and how we addressed it. We also have Kosta Ozapov with us today. He's an engineering team lead here at Scylla. Kosta worked with Kyle to remedy the issues that Kyle uncovered. He also played a leading role in our implementation of Raft. So Kosta won't present today, but he's available for any questions you have about the fixes we made to Scylla or what we're doing with Raft. Okay, without any further ado, I'm glad to hand it over to Kyle. Welcome back, Kyle.
Thank you very much. Hello, everybody. We're going to be talking today about Scylla and Jepsen. My name is Kyle Kingsbury. My pronouns are he, him, and you might know me as Afer from the internet. My day job, terrifically enough, is to break databases. I test distributed systems under different sorts of hopefully realistic failure modes, and we try to see what happens. Do they exhibit anomalies or not? But before I worked on database testing, I worked as a backend engineer at a number of Silicon Valley startups. I worked on APIs, and APIs aren't really concrete objects. You can't go to the store and ask for one API. You can't hold it in your hand and pet it. They're illusions. They're like rainbows, things that we allow customers or users to behold but not to touch. And that API is supported by some actual code that engineers like you and I might write, here represented by these steel girders. And those girders in turn are supported by these wooden pilings, the Ruby VM, the language runtime, libraries, all those sorts of things. And in turn, all of this rests on a firm foundation of open source databases and queues and Redis and things that we found lying around on SourceForge circa 2003 and just hope would work in production. And that's represented here by a pile of tires. Now, as anybody who's ever run a distributed database knows, the pile of tires is usually on fire. And it's our job as good engineers to engage in what's called information hiding. We're going to build a tower of abstraction higher and higher away from the flames so that while our operations staff is screaming bloody murder and throwing more tires onto the pile, customers can still make requests and get responses, and everything should appear to be just fine. In sum, we're trying to make reliable systems out of unreliable parts. Now, when I say databases here, I'm also talking about queues, discovery services, any sort of coordination primitive. These things strike fear and terror into the hearts of engineers because they get into weird cases like split brain, where two different parts of the network believe different truths. Or you have broken foreign key constraints where you go to reference some data and it's not present. Or maybe you have a transient anomaly where you write some data and then can't see it for a while, and then later it shows up again. Now, some people might think that these systems only exhibit these problems in theory. These are academic concerns. In real life, timeouts and decent enough networks mean that we don't have to worry about these problems. But I'd like to know for sure. So I've been working on ways to measure real-world distributed systems, ways that we could put these things to the test and find out if these anomalies actually occur. The most successful product I've worked on so far has been called Jepsen. It's a library for the JVM, which lets you write a test for almost any type of distributed or concurrent system. Like any systems testing tool, Jepsen conceptualizes the world as basically two parts. There's the environment, which is Jepsen and all of its clients and machinery. And then there's the system being tested, which is composed of, say, Linux processes running on Debian operating systems connected by an IP network on top of VMs or containers. All of that stuff, all of those moving parts, should appear to be one coherent thing. If we look at the boundary between the environment and the system, there should be some invariants that hold, some laws. Like if I put an item into a queue, I should be able to read it again. If I'm trying to model my house and my dog Freddy goes out the door, I should expect to see Freddy come back in the door next. If I see Freddy leave the same door twice in a row without coming back in, I know there's a problem. He's learned to teleport, perhaps. So to find these invariant violations, we're going to run a bunch of clients outside the system. Those clients will pretend to be independent actors, as if they were, say, separate users making requests against a web service or separate processes running in a data center. But we're actually going to run all of them in the same JVM Linux process. And the reason for that is that we will then have extremely accurate timing information. We know exactly when every client began and completed its operations, and that's critical for verifying real-time safety. So we run these simulated independent clients, and they interact with the database. The database itself typically runs on 5 nodes. For ScyllaDB, we often tested with up to 10. And those database nodes are actually opaque. There are ways to analyze distributed systems where you do, say, a model. So you would write down the algorithm and then evaluate the algorithm without looking at the code itself. Or you could do some sort of probe or trace or static analysis of the code base. Those techniques are really powerful and they've got their uses. But analysis of the code base isn't going to help us in all cases. Oftentimes, those static analysis systems are built for a specific language or a specific way of doing concurrency, and they may not necessarily generalize to other production databases. In particular, databases are a performance-sensitive case where people often invent their own ways of doing I/O or concurrency, and it becomes tricky to do the probe and tracing that you'd like to do. So in order to have the broadest applicability across different platforms, we're going to complement those modeling and those static analysis systems by doing simply an integration test. We only look at the outside properties of the system, and we have no understanding of the database itself. Our goal is to verify if, from the perspective of clients alone, the database exhibited some anomalous behavior. Now, this means we are going to miss bugs. Jepsen cannot be complete. The database could exhibit a bug that we just didn't happen to see because we didn't make the right request at the right time. But in a sense, this isn't the end of the world, because we only care about bugs that are bad enough to notice. If a bug is truly significant, i.e. it happens frequently enough and it happens in a way that is severe enough to cause visible damage, that's the bug you really care about as a user. If a bug is super small and only shows up occasionally, and you might not even notice it, then it's not a high priority. So we're focusing our attention on a part of the problem space that deserves the most. So in order to find these bugs, we're going to generate randomized operations, like write the variable x, setting it to 5. We'll send that to the database and we'll get back a response, typically over the network. And that response could be one of 3 things. We could have an okay, we know the operation took place. We could have a failure, and we know the operation did not take place. Or something else could happen. We could have a timeout or an indeterminate message or some sort of error code we don't understand. In those cases, we'll flag the operation as indeterminate. We'll leave the invocation open for all time and log an informational message. The reason why we have to leave the invocation open is because the operation may have already occurred. It might still be in flight and occur later, or it might never occur. We can't distinguish between these cases. Any kind of distributed systems testing tool is going to have to reckon about these 3 classes of operations. So we try to be careful about that in Jepsen. Over time, we build up a concurrent history, a sort of tapestry of reads and writes, appends and dequeues, and all the different operations the system can do. Every process is adding things and completing operations, and we tag them with okay or fail or info. Given that big data structure, this tapestry, we could then start to ask questions about the safety of the system. For instance, if we're testing a linearizable system, i.e. one in which operations appear to happen atomically in total order, consistent with real-time order, we need to find a path that connects all of the OK operations and optionally some of the crashed ones. And that path needs to always move forward in time. And along that path, the laws of some data type have to make sense. So we could search through all the different ways of connecting these operations, all the different paths. And if we can find a successful one, we know the system's linearizable. The kind of analysis we did for ScyllaDB is a little bit different. Sorry, Scylla is a little bit different. We used a tool I've been working on for the last couple of years called L, and L is a research project based on cycle detection. In short, we're going to try to identify dependency cycles between transactions, and those cycles will correspond to anomalies in the system. The kinds of dependencies I'm talking about are of 3 classes. We have write-write dependencies, in which transaction T1 writes some version V1 of an object, and transaction T2 writes version V2, essentially overwriting V1's write. So that's a write-write dependency. Somebody changes the thing you changed. A write-read dependency is when the first transaction writes V1 and the second transaction reads V1. So the second transaction saw the first one's effects. Of course, the second one has to happen later. The third class of anomaly, something's called an anti-dependency. is a read-write dependency, where transaction 1 reads some version and transaction 2 overwrites that with a later version. In this case, the first transaction has to execute first because its observed value is going to be overwritten. All of these things come directly from Aj's formalism for isolation levels, and they assume that there is a total order over versions. I'm going to write that as v1 double less than v2. Now, a strange thing happens here because we've talked about versions 1 and 2, but that's not what you get out of a database when you make a query. When you ask a database, show me the current value of object X, it just tells you typically a value, like X is currently 5 or X is currently 3. We have no way to determine whether 3 or 5 came first in the version order. Either one of these could be the case. So this makes it really tricky for us to identify anomalies in the system because we don't know what the version order was. The key insight in L is that under certain conditions with certain data types, we can reconstruct the version order and we can map from versions back to write operations. So what we're going to do in these tests is constrain ourselves to objects which are comprised of lists. So every object has a list of integers, and our writes are only appending an integer to the end of the list, and every write appends a unique integer. That way we can map back and forth. So if I have an append x3 operation and x is currently 1, 2, the new value of x becomes 1, 2, 3. If we see a 3 at the end of the list, we know the append x3 operation produced it, because the append operation always puts things on the end. And if we see a value like 1, 2, 3, we know the previous value was 1, 2. Well, that's cool. We can kind of go both directions now. In fact, if we ever see a read, say we perform one single read at the end of the test, and we see the value of some object as 1, 4, 3, well, in that case, we know the previous value was 1, 4, and before that, 1, and before that, empty. So we can extract the entire version history from any single read. And we can then map that back to the transactions. So if I see these two transactions, T1 and T2, where T1 appends X1 and T2 appends X2, I can look at this later read that T2 performs. It's T2 observes X is 1, 2. That tells us that the append of 1 happened before the append of 2. So we can infer a write-write dependency there. We can also infer that T2 observed its own previous append. Append X2 appears in the read of X1, 2. And we also know that because that read of X1, 2 does not include the value 3, that T2 must read-write depend before T1. So we have a cycle here. T1 needs to execute both before and after T2. These things cannot be totally ordered, and the system cannot be serializable. This is the technique we're going to use inside of Jepsen for testing Scylla. And in particular, it allows us to identify almost all of the anomalies described in Aj's formalism. We can find write cycles, aborted read, intermediate read. That's where you see a value that was written by an aborted transaction, or you see a value from the middle of a transaction. Cyclic information flow, which is a cycle entirely composed of write-write or write-read edges. Read skew, which is a common anomaly that's supposed to be prevented by snapshot isolation. Even anti-dependency cycles, a repeatable read violation. And we can find more anomalies that aren't specified in the formalism, things that should never happen in databases, ideally, like garbage reads. You read some value that nobody ever wrote. Or incompatible versions. If we could prove that no total order of versions exists, that tells us something is really wrong in the database. We could see internal consistency violations where a single transaction fails to observe its own prior effects. Or we could have duplicate writes where you do a transaction once and you get multiple copies. All of these things can be done in a single pass, given just our data structures of lists and transactions that append things to them. Now, there is a proof which tells us that serializability verification, like linearizability, involves finding all of the permutations of transactions and checking them all. And that's going to be on the order of n factorial. This is solidly in X time. However, if we constrain ourselves to this particular world of lists with append, we can do this analysis entirely in linear time, which is great because the exponential time algorithms crash and burn after about 100 to 200 operations, depending on complexity. So to recap, our general approach in testing databases is to generate randomized operations, apply them to the system using network clients, and then to record a history of their operations. So we get all the invocations, all the completions. And then with that abstract history, we're going to verify that it's consistent with some model of the system. We're going to look for cycles. We're going to try and find a path through the history. While this is going on, we're going to get out our network shears. We're going to cut the network into pieces. We will introduce clock skew. We will kill and pause processes. We will add and remove nodes. We'll issue decommission commands, all that good stuff to see what the system does under stress. So let's talk about Scylla and what we found. This is work that began in summer of 2020 on version 4.2 RC3, and it completed in fall of 2020. So these results are a little bit stale by this point in January. And we're going to talk about the things that were fixed and what the current behavior is as well. If you're familiar with Scylla, you know that its proposition is basically Cassandra, but faster. It's written in C with some libraries for speed. I can't speak to Scylla's performance characteristics, but this is the goal. Like Cassandra, it is a wide column store, which means it's a row store where every row could have an arbitrary number of columns. It offers eventually consistent defaults, up to AP, every node being available if you use read and write consistency of 1. And it also has an optional Paxos transaction system we'll talk about later. The key unit of data in ScyllaDB, like Cassandra, is a cell, which is essentially a triple of a key, a value, and a timestamp. So here we have a cell representing somebody's name. Their name is Octavia, and their name was written specifically at timestamp 3. A row is a collection of cells. So here we have a row representing famed science fiction author Octavia Butler and her books, which include Bloodchild, Parable of the Sower, and so on and so forth. There's a system called CQL in Cassandra and in Scylla, which maps data structures like lists, maps, and sets into cells. So this array of Bloodchild, Parable of the Sower is represented as a single key in the logical row, but under the hood, it's mapped to several different physical cells, one for each entry. We'll talk about why that is in a second. Rows are arranged into tables. A table is a big sorted collection of rows, and then it's split into partitions. Each partition is kind of the unit of replication and atomicity in Scylla. So the Paxos state machine is attached to the partition. The partition is the thing that gets migrated from one place to another. That's the sort of shard. Now, the way of resolving conflicts in Scylla is called last write wins. And in this approach, we look at the timestamp given two different replicas or two different versions of a value, and we pick the one with the highest timestamp. So here, given two values, dog sleepy, dog playful, it doesn't actually matter which one's written first. The one that wins is dog sleepy because it has the highest timestamp. This results in interesting behaviors. For instance, if we have an initial value in ScyllaDB of 0 at time 5, and the client on the left reads that 0, adds 1 to it, and writes it back, the client on the right reads 0, adds 2, and writes that 2 back, well, the version of 2, if it has a lower timestamp, will be destroyed in favor of version 1. If the timestamps are reversed, then 2 would win instead of 1. But either way, we will have lost information. Concurrent updates to Scylla can result in lost updates. In this case, 0 plus 1 plus 2 is equal to 1. This is, in a sense, an anti-pattern for ScyllaDB. You're not supposed to modify things in place in this way. Instead, you should be journaling your updates to separate cells or using some sort of commutative structure where this is safe. For instance, a CQL collection, which means you can do a bunch of list appends or set inserts and have them all commute together instead of clobbering each other in place. At least that's the goal. Let's try it out. We'll create a table called sets with an integer primary key and a value who is a set of integers. Then we're going to insert a single row into that table, which has key 0 and value being empty set. After we've inserted that initial row, we'll perform a bunch of updates where each update sets the value to be the current value plus a singleton set containing a unique element. So we'll add 1 to the set where the ID is equal to 0. Now, we did this in strict order, so the insert always happens before the update, and we're going to use consistency level all, which is the strongest of the classical ScyllaDB consistency levels. You would expect that adding 1 to the empty set would result in the set 1, and you'd be right most of the time. Sometimes in our tests, we'd get an empty set, and that's a little surprising because set addition should theoretically commute. This happens if the client performing an insert gets a higher timestamp than the client performing the update. The update is ignored in favor of the original insert. If the opposite history happens, where the client performing the update happens first, but it happens to get a lower timestamp than the client performing the insert, then the insert actually deletes the update. It destroys everything with the prior lower timestamp. And both of these operations take place in a way that looks to be successful. The client has no idea whether they logically took place or not. It just knows, yeah, your thing took effect, but it may have been silently discarded. There are three factors that make this surprising. One of them is, of course, Scylla is not linearizable, and we shouldn't expect it to be. Linearizability would mean that things take place in real-time order. So thinking about the order in which we actually sent the operations to Scylla and expecting that to be the same order they logically take effect, that's not a thing. We shouldn't expect that unless we use LWT. The second thing that makes this surprising is that insert and update carry some semantic sense from our history of using things like SQL of being different operations. We usually think intuitively of an insert as only inserting if there's nothing presently there. And we think about an update as changing something that already exists. But in Scylla, like Cassandra, both of these are basically the same operation. They're both essentially an upsert. As a result, it's easy to write code which looks like it should be safe, but actually performs two upserts, one of which destroys the other. The third thing that makes this surprising is that if you're used to other eventually consistent data stores like Riak or AntidoteDB, things that use CRDTs, set inserts in those systems typically commute. You would not expect to have a deletion. But the way that this is built in CQL is that inserting an empty set actually creates a deletion tombstone for all set elements with lower timestamp. I think the reason this is done is because it's intuitively correct. People wouldn't expect insert empty set to not produce an empty set. And as long as your timestamps are sufficiently well ordered, this is all going to look fine. But when your timestamps happen close together, then it can create weird results. So the documentation actually suggested that you do this. Like if you read the DML documentation circa fall of 2020 for Scylla, it would tell you, okay, insert a row and then demonstrate doing updates in place. And it didn't necessarily note that that could be unsafe. And in fact, this bug slipped by the Cassandra engineer who worked in the test originally. It slipped by the Scylla engineers who ported it to ScyllaDB. It slipped by me. I was staring at this bug like, where is this coming from? And then more Scylla engineers kind of cocked their heads until finally one Scylla engineer caught it. They said, oh yeah, you can't perform that insert. That's unsafe. So I thought, this is surprising. This is my job. I'm supposed to be good at this. And I'm thinking usually about asynchronous and commutative operations, but I didn't catch this. Does anybody? So I made a little survey and I sent it out to folks on Twitter saying, hey, if you use CQL, what do you think this does? Not one person correctly predicted this outcome. My favorite response simply said, I feel bad when they learned what happened. It's surprising that this fact of Scylla, which has been so long documented and which we all should have internalized by now, still manages to surprise us. But in a sense, there's nothing new here. This is an old result. We all know this is how Cassandra and Scylla should be working. And so there's nothing really to complain about. The documentation in other parts of the docs told us this could happen. Well, the Scylla documentation for DML, the walkthrough, now gives you clear examples of working with CQL collections, which I'm hoping will highlight this challenge for users. And I think that this might help us build safer applications. If you don't want to have this problem, if you don't like having to reason about the possible implications of non-commutative updates to collections, then you should be using LWT, lightweight transactions. These are backed by Paxos, a consensus algorithm. And if you're familiar with Paxos or Raft or Zab, in most cases, it takes 1 round trip for consensus. ScyllaDB takes 3 round trips. Cassandra takes 4. So be aware that these transactions might be 3 times slower than you're used to in other systems on a latency basis. That doesn't mean they're impossible, though. Data center latencies are often on the order of 1 to 10 milliseconds, and so it's perfectly reasonable to execute a few of these transactions in the context of a live request for lots of applications. You also need to be aware that lightweight transactions are quite lightweight. You can perform only certain types of operations, like an insert, update, or delete with a conditional, there's no way to express one without a conditional, which makes it tricky to do writes in place. You could also do a select of multiple keys if you specify a key in key 1, key 2, key 3, but you can only do that select if you're not trying to read a column that has a CQL collection in it. If you do that, then the where k in syntax is rejected. You could also perform a batch write, where you could do multiple updates, deletes, inserts, but you can't read anything in a batch. So it's a little bit tricky to write generalized transactions in this framework. The other thing you should be aware of is that because all of these take place only within a single Paxos state machine, which is scoped to a partition, you can't express these queries across multiple partitions. There's no notion of a cross-shard transaction. So we tried this out, and we found aborted reads. This is bug 7258, and it occurs when you have process crashes and network partitions. We'd append an object, append like a number 52 to a list, and we get back an unavailable exception, not enough replicas available for query. And if you go to the documentation for this unavailable exception, it looks like it's saying, well, this happens when you can't even reach the a majority of the other nodes in order to begin the transaction. So you think this means a definite failure, but it actually doesn't. Sometimes you'll issue a select query and that operation that supposedly failed is actually there. So this is a bug, arguably, in the way that timeouts which happened later in the Paxos state machine were handled. They were surfaced as unavailable instead of write timeouts. Now, in Scylla 4 through RC1, they're returned as write timeout exceptions instead, which should mean that you don't, if you catch this exception and you handle it appropriately, you won't have to worry about aborted reads. Bug 7113 involved batch updates with transactions. When you perform a batch, like updating keys 1 and key 2, the return value is undocumented. But if you look at it, it looks kind of like you'd expect. It's a collection of rows which say applied true, key 1, and then a couple of fields telling you what you changed. And then another one for key 2. So you might write some code that performs several updates in a batch and then looks at the results and tries to figure out what happened to each update. If you're not careful, you might not notice that the key order is unspecified. So you might get back keys 2-1 or keys 1-2. You need to look at the keys and map them back to the keys you tried to update. Or you could get just key null. This happens because the values returned are the prior values rather than the resulting values. And if the row didn't previously exist, it would have a null key. So in this case, we have to assume that both key 1 and key 2 were previously null. Sometimes you get just key 1. And this was a bug where it would discard a null value accidentally. So all of these issues have been addressed, and Scylla's made an API change. Now, when you make a batch query, you get back your results in the order that the batch specified them, which makes it really easy to map back and forth between what you asked for and what happened. Bug 7170 involved isolation issues in non-transactional workloads. The Scylla documentation says that insert, update, delete, and batch were isolated and atomic. And if you're thinking about atomicity and isolation in the context of a database, you're probably thinking about that ACID acronym. Isolation ACID often means serializable. So transactions should appear to take place in some total order as if they executed one at a time. You don't want them to interleave with each other or appear to execute concurrently. However, we can, just by thinking about it, conclude that this cannot be the case for CQL collections. For instance, imagine that we have a single collection, an empty set, and there are 2 replicas, S1 and S2. If one replica adds 2 to the set and another replica adds 1 to their copy of the set, then it's possible that reads against those 2 replicas could observe the set 2 and the set 1. It is impossible, if all you're doing is adding elements to a set, to execute those adds in total order and observe just 1 and just 2. You should always see something like set 1, set 1, 2, or set 2, set 1, 2. So we know that isolation can't hold for collections, but this isn't just a problem with CQL updates. This is also a problem even with batch operations that do straight up writes, or if we do a write of a single row and we change 2 different columns in it. So let's imagine that we write a row and we always set 2 columns or 2 fields, X and Y. We'll set them to +1, +1, +2, -2, -3, -3, anything where they have the same absolute value. Then we're going to do a bunch of reads of x and y, and we should always observe something like +7 -7 or +8 +8. They should always have the same absolute value because those writes are theoretically atomic and isolated. But sometimes we observe +7 -3, which is clearly an isolation violation. This is an x from one transaction and a y from a different transaction. And this occurs even with consistency level all, the strongest of the classical Scylla or Cassandra consistency levels, the default atomic monotonic timestamp generator. This occurs in healthy clusters with no faults and with perfectly synchronized clocks. Indeed, synchronized clocks kind of makes this problem worse. And the reason is that we have collisions in timestamps. At 500 reads per second and 500 writes per second, we were able to observe isolation violations roughly every 20 seconds. So this is not super common, but it does happen when two timestamps collide. If client 1 tries to write x1, y -1, and client 2 tries to write x -2, y2, and both of them choose timestamp 5, then Scylla will resolve these writes not on the basis of the entire write operation, but on a cell-by-cell basis individually. So it looks at the cell for x and says, well, I've got two copies, both of the same timestamp. One is bigger than -2, so let's keep x = 1. And then it looks at cell y and says, well, y both have timestamp 5. I've got +2 and -1. 2 is bigger. So now we've preserved the x update from one client and the y update from the other and violated isolation. This isn't news. We reported exactly this problem in Cassandra in 2013, 7 years ago. Cassandra reported it again in their own bug tracker in 2014. It can be caused by read repair in addition to timestamp collisions. Scylla reported this issue in 2017, and there are still, to this day, open issues in Cassandra around providing proper row-level isolation. And yet, the Cassandra docs continue to insist, 7 years later, that writes are performed with, quote, full row-level isolation, which is a blatant lie. I'm not sure why this persists, but because the Scylla documentation was sort of extracted from the Cassandra documentation, a lot of these claims made their way into Scylla's docs as well. So the good news is that Scylla has updated the documentation. They no longer claim isolation. And now there are extensive examples of what happens when timestamps conflict. And I'm hopeful that this will help users make better decisions about how to manage their updates. In particular, I should mention that this makes it impossible to, without using LWT, write two fields that need to be read together in a way that is safe under contention. So if you wanted to write, say, a password hash and a password salt into two different cells in the same row, you can't guarantee that you're going to get the salt that goes with the right hash. You might get a salt from one password and a hash from another. So really do keep this in mind. All right, bug 7116, lightweight transaction stale reads. We could write a value like 6, and the write would complete. We go on to write a new value like 7, and we could read that value 7. At this point, using transactions, we should definitely not be seeing 6 anymore. We've moved on to a new value. 40 seconds of reads and writes could occur, and then suddenly a read would observe 6 again, this blast from the past. This happened even without faults in healthy Scylla clusters with single reads and writes, not even trying to do multiple updates. In one of our tests, out of 1,100 transactions, 260 of them were involved in one single massive isolation violation of real-time safety. So what gives? I mean, this is a little weird, but it's also not the end of the world to see a prior value, right? This is a state that was valid at some previous time. But then we started to see weirder phenomena. For example, we'd be appending to a list X. We have 17, 18, 19, 17, 18, 19, 20. And then a prefix of the list would disappear. So we go from 17, 18, 19, 20, 22 to just 22. And then the prefix would reappear later. That's really strange. That definitely shouldn't happen if all we're doing is appending to the list. Or we could see a tail of the list fluctuate between two different values. So depending on what replica you talk to, the list always starts with 2, but the end of the list could be 614 or 12. And then later on, they get like glued together in some way. Very strange, definitely not linearizable. This happens in healthy clusters, even with serial reads and with LWT writes, so the strongest possible safety levels. This was due to an improper hash calculation inside of Scylla. When Scylla needs to look at two rows and determine if they're different or the same, it takes a hash instead of comparing the actual values. And the hash code calculation would stop looking at the row once it hit a null column. So if we had two rows that were identical up to the null field and then differed in later fields, Scylla would consider them to be equivalent. And then it would allow you to have these divergent replicas for some time. That's now been fixed as of version 4.2. We found several issues in membership changes. And membership changes are notoriously a difficult thing for databases to do correctly. They're extremely gnarly. In Scylla, we would see behavior that looked like a classic split brain. So depending on what replica you read, you could see two completely different histories of a list that evolved independently. Or you could say append 9, 10 on one replica, and then append 11, 12, and 13 on another. And you would expect if this were linearizable that you would read 9, 10, 11, 12, 13, but the 9 and 10 would not be visible. And then somehow 11, 12, 13 would get appended to a different replica, and that replica would show you 9, 10, 11, 12, 13. So we'd see weird issues with like unidirectional replication, writes being visible on some cluster members but not on others. Very strange. This is due to three problems. One of them is that repair processes in Scylla could, under some conditions, only read from a single replica, not from a majority. So here, node R is taking data from S1. It's repairing, getting all sorts of information, but it doesn't know about writes that are happening on the majority replicas, S2 and S3. That's been fixed in 829b4c1. There's also an issue with the way that list operations are mapped to underlying cells. They would choose keys for the cells, which are based on the local clock of the node executing the operation, not the transactional timestamp. And that could lead to weird ordering issues or maybe collisions. They're working on resolving this, but it gets tricky when there are multiple appends because sequentially allocated lightweight transaction timestamps, you can't use timestamps 1 and 2 because the next transaction might use timestamp 2. So this is, I believe, still in progress. Membership changes in our testing were also performed concurrently. So some of the time we'd issue a remove node, and then we'd issue an add node while the remove node was still in progress. And this is common for tests of distributed systems that I've done. A lot of times when you're handling a cluster with failing members, you don't exactly know what's going on because some nodes are up, some nodes are down, there's partition. And so you wind up with occasional concurrent updates. And this is unsafe in ScyllaDB. Scylla says that you have to ensure that all previous membership operations have completed before you start a new one. The obvious question is, how do you ensure this? And as far as I can tell, you can't. Not in generality, anyway. There's no API you can call that will like block until your membership transition is completed. There's no way to return the status of it reliably. I think the way you have to do this is by requesting node tool status on every single node. So you can't do this when nodes are down or unavailable. So really be careful. Look to make sure that all membership operations you've done in the past have completed successfully before you move on to a new one. The other problem is that we followed the documented path for node tool remove, which says you can check the status of the node. So we'd ask node A, hey, is C down? And it'd say, yeah, C's down right now. Then we'd issue remove node for node C, sending it to node A. Now there are two possible outcomes here. One of them is a race condition, right? We could see node tool status down and then C would come online, or C could just be partitioned, so A couldn't see it. In either one of these cases, C could still be alive and possibly executing transactions. In fact, C might even be in the majority component, but A can still try to remove it. And that leads to all sorts of weird split brain issues. You must kill or shut down a node before moving it. That means asking EC2 or VMware to make sure the VM is really terminated. You have to make sure there's no like fallback copy of the node somewhere else. You need to go turn off the power or like log into the machine and make sure the Scylla process is dead. If you can't reach it, you can't remove it. These are sort of surprising constraints. For one, most databases don't or shouldn't require this. And for two, this wasn't documented. So as far as I know, users had no idea they weren't supposed to do this. It's just something you had to sort of magically intuit. But the good news is that Scylla has now added documentation that says you need to do these things. So users can now be aware of these surprising operational challenges. As of January 15th, 2020, we found 7 issues in ScyllaDB. 5 of them have been patched or documented, and 2 of them are pending. What's left is mainly around membership changes. In particular, the concurrent update to membership that we saw, that constraint is now documented. And once the Raft implementation takes over for Scylla membership, this probably should disappear entirely. Part of the reason why we saw these membership problems was because the cluster membership state in Scylla is managed by a gossip system, which is eventually consistent. Yes, as of January 15th, 2021, thank you. I can write. 2020 is lasting forever for me. Membership changes are documented. The cluster membership state is stored in the gossip system, which is basically inherited from Cassandra gossip. And the gossip system is eventually consistent, which means that nodes can disagree on who's in the cluster and who's responsible for a piece of data. So it doesn't necessarily matter if you have a Paxos system. If the Paxos system doesn't know who the nodes are even supposed to be, that makes it challenging to safely execute transactions when membership changes are undergoing. However, the new Raft-based cluster membership system should resolve this by giving every node a consistent snapshot of what the state is supposed to be, who the replicas are, who owns what data. The final thing I want to note for Scylla in particular is that timestamps are notoriously tricky to deal with. Even for people who have theoretically been doing this for years and should know better, they can still be surprising. If you need ordering or isolation between your operations, you probably want to be using lightweight transactions for those things. To recap, when you are intrepid database operator, choose a database, you are essentially signing a contract. Whether you actually purchase it or just pick something from the open source freeware web, you're locked into a database for a while because it takes time to change the APIs and change your use patterns. So make sure you read the documentation, that contract, really carefully. Look for places where the contract makes interesting claims, like you need to kiss the prince by the 3rd day or your data is forfeit. Look out for those cases. And then throw away the docs and test it for yourself, because it turns out that a lot of times the documentation is just flat out wrong. Look out for words like strict consistency, strong consistency, acid. These are sort of weasel words. They sound great, but acid can mean anything, well, at least the way it's used in industry. It could mean anything from like read uncommitted all the way up to strict serializable. There's a huge swath of behaviors that can be included in this word. So make sure you look for a specific formal guarantee in addition to those buzzwords. I want to encourage both users and vendors to brush up a little bit on their consistency models and to be specific in what they expect and provide. Look for the invariance system actually needs. Plenty of databases can lose data and be just fine, as long as the data loss probability is relatively low. Ordering violations, those weird anomalies where lists flicker back and forth, sure, they've probably been happening in real-world Scylla deployments, but people may not have noticed because the data that was being manipulated just didn't matter that much. So you only need to care in certain cases. Try to focus your attention where it's really needed. I always tell database vendors to use proven algorithms, and Scylla, like Cassandra, has done a great job of using Paxos, a well-designed, well-studied formal algorithm or family of algorithms for consistency. However, proven algorithms don't actually solve all your problems. Even though the Paxos implementation in Scylla looked to be correct, the node membership that it was using, that was stored in Scylla gossip and was unstable. So we need to test not only the model and the algorithm, but also the way that things are plugged together. When you're doing database testing, look for your failure modes. Look at process crashes, which you can simulate with kill-9. Look for node failures, which you can simulate by terminating instances or flicking the power switch. Look at clock skew, and this is particularly important for applications using ScyllaDB because your client clocks are what control safety. So try messing with the clock, setting them to hundreds of years in the future or a few seconds in the past. Use fake time to lie to your process's LD preload shim about the times. You can test garbage collection and IO pauses with sigstop and sigcontinue. And you can test narrow partitions, which I think are one of the best tools we have for testing distributed system safety with IP tables -j drop, or using TC to introduce artificial latency into packets. Narrow partitions are particularly useful because they create large windows of concurrency. They delay packets long enough that an observer can get in there and see an anomaly as it's actually happening. It's not enough to test systems individually. I think we need to test them end to end in addition to their components. And that testing in Scylla has proven fruitful. Ultimately, I'm suggesting we as an industry, both vendors and people who write systems on top of databases like Scylla, should be doing a little more property-based testing. That means coming up with random inputs instead of writing them down by hand, applying the inputs to the system, and then verifying that some high-level invariants, some laws hold. Now, I've talked about how to verify things with L, which is the transactional isolation checker looking for dependencies, but you don't have to be that sophisticated. If you're building a user registration system, for instance, you could consider an invariant to be 2 users can't register the same username. Or maybe if you set your password and it writes 2 fields, you should always be able to log in with that password again, and the 2 fields should be consistent with one another. When you're doing this testing, you have to do it with distributed systems failure modes, because real world databases can and do exhibit all kinds of weird behavior because computers are awful. Finally, if you look for perfect databases, you will never be content. Building any kind of distributed system is an incredibly difficult undertaking, and the folks at ScyllaDB have made a really good shot at this problem. So I want to give them a round of applause for taking the time to look for these bugs with me and fixing all these issues. This work would not have been possible without my research collaborators, Peter Alvaro and Kit Patella. Kit in particular wrote one of the first implementations of L. ScyllaDB provided the funding for this research, and many of their engineers collaborated with me on it. In particular, I want to thank Camille, Peter, Piotr, Dor, Duarte, Konstantin, Alejo, and Pavel, all of whom were a big help putting this work together. Kostya in particular is basically responsible for all of the good stuff in this report. I only find the problems. He actually figures out what's wrong. Thank you all very much for taking the time to watch this talk. If you want to read more about this, there is a full report on jepsen.io. At this point, I think we'll open it up for questions.
That's great. Thank you, Kyle. I really enjoyed that. Well, as Kyle said, let's go to the Q&A. We've already received a few really good questions. Any other questions, please use the Q&A button down at the bottom. And I've got a great one for you, Kyle. Here it says, what are your future plans for L and Jepsen? And I'll remind folks L is the consistency checker.
Yeah, so Jepsen has been basically stable for a while now. I'm adding lots of ease of use improvements, performance changes, bug fixes, but the core ideas seem to be solid and applicable to a wide variety of systems. L, on the other hand, is definitely incomplete. In particular, I have no idea how to check predicates. Now in Scylla, this is not a problem because there's no notion of a predicate query, but in a lot of databases, you can say, give me the set of all houses which have a dog, and do some operation on that set of houses. Well, that kind of predicate-based operation could fail to be consistent in a way that individual key value operations don't. And I'm trying to figure out, how do you write down that formalism and then verify it?
That's great. And I'll remind folks that we also have Kostya. Kyle just mentioned Kostya as having been involved very closely in fixing the things that Kyle discovered, and he's available for Q&A. And I do have a question for him around Raft. And Kostya, that's how does the overhead introduced by Raft compare to lightweight transactions with Paxos?
Hi, I actually also see a question in the Q&A part, and it sounds relevant to the question you have. Why do LWTs take 3 round trips right now? And I think I should begin with that one. So typically Paxos, as Kyle mentioned, takes 1 or 2 round trips, and we take 3. And I try to sort of explain this try to explain this in one of my talks. The LWT is built on top of eventually consistent Cassandra tables, and to make them both work together, eventually consistent writes and strongly consistent writes, The way LWT is carried out is it's first fully carried out outside the base table. So these are the two standard Paxos rounds that are used. So the first two rounds are to basically complete the transaction outside the base table, and only when we know it's ready, it's finished in the majority of participants, we apply it to the base table. If you don't do that, LWT might break quorum rights. So something that is quorum applied with LWT will not be quorum readable, say, with eventually consistent reads. So the short conclusion is that for compatibility between eventually consistent and strongly consistent operations, although I would not recommend to use them together still unless you really know what you're doing. So there are some scenarios where it helps, and it can allow you, if you are prepared for, say, a bit outdated reads, a bit outdated data, to read with quorum and write with LWT. Certain scenarios are tolerant of these sort of relaxed consistency levels, but generally, it's not a good idea to use eventually and strongly consistent operations together. So in that sense, we had no options but to be compatible with Cassandra. We want to be as close to them as possible for the operations that are implemented there. And now to Raft. So with Raft, it's a completely different story. We don't have to have that semantics. We can come up with the semantics that would be strongly consistent, but would be specific to Scylla. And this is why Raft can be much, much faster than LWT. So a short answer, it's going to be at least 3 times faster. But it can be, depending on the quality of implementation. In my measurements, we can get at between 3 and 8. So let me explain why. First of all, LWT uses a system table for its log, for its Paxos journal. And when you write to the system table, you essentially write both to mem table and to the base table and to the commit log, and you compact that base table. So a typical Raft log would go directly to a file. And here you first write to the mem table, then you write to the base table, and and when you write to the base table, you also write to Scylla commit log. So there is a 3x write amplification just from using a base table for Paxos commit log. Another level is, of course, the number of rounds. You do first you do the prepare, then you do the commit, and then you write to the base table. Nothing like that in Raft. In Raft, you write to the commit log. As soon as you get the majority of writes to the commit log, you can apply the record to the base table. So, it's like 3 times less. And finally, the compaction or I would say recycle or expiration of the commit log can be done much faster. If with LWT, you essentially you write a tombstone on the previous commit log record, and then it's compacted out. With Raft, you can simply recycle commit log segments. It's a challenge, though, to do that as efficient as I described with Raft, because in Scylla, we are going to run multiple Raft instances, even per a single shard. And so if we just literally do it like that, it's going to be many files even on a single shard, every file for a single Raft instance. So we are now looking at overlaying multiple logical Raft logs over a single physical journal. We begin by still storing this in a base table. So because a base table is just a good way, so a single partition of a base table could be, say, represent a single Raft group. But going forward, we are going to move it from the base table down to the more efficient storage. So between 3 and 8 times.
That's great. Thank you for that, Kostya. And I'll remind folks, the Kostya did a whole session on Raft at our Scylla Summit. All the sessions from our Scylla Summit are available from our website. You can see recordings of them there. And you can also ask us questions on our Slack channel. Sign up for our user Slack for any other questions you have. I'll go to a question for Kyle. Hey, Kyle, I believe Jepsen is a state-based method reducing the history of events one by one and looking for invariant violations at each step. Do you have any suggestions of how to express invariance solely on the history of events without building an intermediary state?
Short answer is no. It does not reduce step by step. The implementation for checkers is completely up to you. You're given the history as basically a big array of all of the operations, and then it's completely your choice how to go through it. For some simple checkers, you could go through stepwise. So build up an intermediary state and just kind of reduce over the whole array. But for other systems like L, we will split up the data set by key, and then we'll build separate indices and try to extract the version dependencies for each key separately. Then we merge those things together. And there's a lot of like parallelism and sort of fork join stuff going on there as well. So yeah, you can build things with intermediate state, but a lot of checkers actually do something more sophisticated.
Here's another question for you, Kyle. It's, hi, is Scylla tested with VMs with bonded interfaces or other than XFF's file system where the typical Scylla setup fails and we have to work around these manually? What is the penalty when we do these workarounds?
I imagine you have a, go on.
I think this one is.
I think that's for you, Kostya. Yeah,
it's for me. Yes, it's a difficult question on Scylla, running Scylla in production, and even I, had to scratch my head to collect an answer for this. So,
let me make a suggestion, Kostya. Why don't we, Raji, who asked the question, Raji, why don't we follow up with you after the seminar? We've just got a couple of minutes left, and we'll connect you to Kostya and get an answer for you there. Is that fair?
And just as a quick note, the tests that we did for Scylla and Jepsen were running on ZFS and ext4, both in Linux containers shared on one host and also in separate EC2 M4X larges, I believe.
Yeah, so the short answer, if you're focused on performance and specifically on LWT performance, XFS is strongly recommended. And I can explain why a bit later.
Okay, thanks for that. We'll end with one last question, and this is a pretty broad question. Any extra comments on the future implementation of strong consistency? Another long answer, perhaps.
Yeah, so we have only 2 minutes. There are lots. There are some. I guess we need to deliver. That's like the short answer. There is a lot of features that can be improved with strong consistency, materialized views, schema changes, topology changes. I hope you'll learn about them from our release announcements, not from webinar about the future. So that's what I'm here for.
Yeah, that's great. And Brian, we'll follow up with you as well for a longer answer around that. Well, at this point, I'd love to thank Kyle for your time today. Thanks for joining us again, Kyle. Kostya, thank you for your time. And thanks to our audience for joining us today. As we said, we will send you the slides and recording of this webinar. Please do join future webinars. And I'll remind you again, all the sessions from our Scylla Summit are available from our website as well. Thank you again for joining.
Thank you.